Hello, my name is Dane Schollen, and I'm going to be covering gravitational potential energy, the derivation of the equation, its application in planet and satellite systems, and inside of planets, and escape velocity. So let's get started. So let's see here. The potential energy. So a couple chapters ago, we covered potential energy of objects at certain heights above the Earth. So in a conservative force field, which gravity is a conservative force field, the negative work required to go from point A to point B is the potential energy. So we would write that as, delta U is equal to mgh, and where h is y1 minus y2, or the height above the Earth. So this is the change in potential gravitational energy, and it works when the h is small relative to the radius of the Earth, which is the case at about the surface of the Earth. But when we're talking about smaller or larger systems, such as the Earth and the Moon, we have to take into account that gravity drops off as the radius increases. So we will start with U is equal to work. So potential energy is work. And work is the summation, or the integral of the force over some distance. And delta U is U final minus U initial. So Newton gives our gravity, or our force of gravity equation earlier in the chapter as Fg is equal to big G times little m, big M over r squared. So when we apply that to the integral, we get the delta U is equal to the integral of r initial, or from r initial to r final, of Fg dr. So we plug in the law of gravitation here, and we get delta U is equal to integral r initial, r final, of big G, little m, big M over r squared dr. So now let's go ahead and do the integral here. Delta U is equal to Gm, and we'll go ahead and make this for the Earth. From our initial to our final. And I'll go ahead and plug in those. Negative G, big M, Earth M, 1 over R final minus 1 over R initial. So that is our equation for delta U, but we want the total potential energy of an object outside of the Earth. So we're going to go ahead and set our reference point from U is equal to 0. So this simplifies to U is equal to big G, mass of the Earth, times little m. Oh, yeah, okay. This is a negative, actually, over R. So this is our equation for gravitational potential energy for an object outside of a celestial or planetary body, specifically in this case the Earth. It can apply to any planet, though, as long as you know that what the mass of the planet is and the radius from your object to the center of the planet and the mass of the object. Okay, so let's talk about a planet-satellite system where we can use this equation. Okay, so when we have a planet and a satellite, so like a geosynchronous satellite in orbit around the Earth, we're going to go ahead and consider them as one system. And within a system, energy is always conserved. And in this system, the motion of the larger body, so the Earth, because of the force of gravity of the smaller body, is very negligible. So that means that as the satellite rotates about the Earth, it's not moving the planet very much because the difference between their masses is so great. So that means that the total energy of the entire system boils down to E is equal to K plus U of just the satellite. So that can be expanded as 1/2 mv squared minus g m little m over r. So what's important about this is that there is a clear relationship between the velocity of the satellite and the radius it orbits around the large body. So when the radius changes, the velocity has to change accordingly to keep the energy the same, which means you can figure out what the change in velocity is when the satellite drops to a new orbit. Something that's, nope, that's all I had to say about that. Okay, well, let's move on to escape velocity then. Okay, so in order for an object to escape the gravitational pull of a planet such as the Earth, it must have enough initial velocity to get to the point where there is no more force acting on a very negligible amount of force acting on the planet or the body that is escaping from the Earth. So you can never really get to the point where there is no force, because that would be an infinite distance away from the planet, since gravity can extend an infinite distance. But we at least assume that it's getting close. So as U, which is the potential energy, the gravitational potential energy approaches zero, so we never actually get there, but we're approaching it. We also want V to be approaching zero, which that just means that we're going to get the minimum velocity we need in order to get to the point where we completely escape, or at least close to completely escape, the gravitational energy of the Earth. Gravitational force, I guess. So that means that K needs to equal negative U. Since U is a negative value anyway, it's a negative energy, this other negative cancels it out, and you have the initial energy of the kinetic energy of the object has to equal the potential gravitation energy it has to overcome. So let's expand this to 1/2 mv squared. Escape is equal to, and our equation for U is big G, and since it was negative to begin with, this negative cancels and we get just regular big G, big M, little m over radius. And let's go ahead and do Earth. So the velocity for escape on the Earth is equal to square root 2 big G big M over radius of the Earth. So this is our equation for getting off the Earth. A couple of things to note here is that the little m, so the object of the thing that is doing the escaping, cancels, and you're left with just the values of the radius of the Earth and the mass. And so if you have both of those values for any planet, this equation, you can find the escape velocity. So the moon would be an example of something you could do this with. And also, it doesn't matter what the mass of the object is that's doing the escaping, so the velocity of a baseball leaving the Earth's gravitational pull will be the same as a couple-ton rocket. Okay, so now let's do potential energy when R is greater than or equal to big R and R is less than big R. And what I mean by R and big R is little r is the distance from U, so, or whatever body is, the small one. That's the distance from that object to the center of the large object, so the Earth would be an example. And big R is the radius of the large object, so the radius of the Earth. So we're going to do this for two different types of planetary bodies. I guess one, it doesn't really exist as a planet, but the first being a solid planet. So when r is less than or greater than or equal to big R for a solid planet, so this is you on the outside, and here's the center of that planet. This is little r, and this is big R. Okay, so you are outside of this planet, and the equation that Newton gives us for this situation is Fg is equal to negative big G, big M, little m over r squared. So this seems a little bit counterintuitive because you would think, okay, here's a bunch of mass over here that is much, much closer than this r seems to suggest. It's like halfway in between here. So wouldn't that have much greater force of attraction, and therefore this wouldn't really be an accurate representation of what the actual force of gravitation is? Well, what's neat about this is that there's also this mass over here that is the same as this mass, and this has the same amount more gravitation than there would be at the center, as this does less. So these two cancel out, and so does all of the mass that's over here and all the mass that's over here. So the beautiful trick here is that when you have a planet such as this, you can go ahead and consider all of the masses being centered at this one point, and this equation works. Okay, so now let's do another solid sphere, but now little r is less than big R. So that means that you're right here inside the planet. So let's go ahead and, this is little r here, that little leg, so I'm going to extend this around. So we can consider this in two parts. We have you here, and there's the mass outside of you, and then here's you here, and the mass that's within the R here. So this mass here is very, very close to you, so it's going to have a great attraction. But this mass over here is further, so it's going to have less attraction. However, there's a lot more of this mass that's over here that has the less attraction than there is the mass over here that has the greater attraction. So they cancel out. So this force is equal to 0. So none of the mass that's on the outside of you actually counts for what gravitation you feel. So the only thing that matters is what is within your radius between you and the center of the planet. So the equation we get is Fg is equal to negative big G m big M over r cubed times little r. So this equation gives us the force of attraction of just this mass that's in here according to your r, the little r, from here to here. And it's related, I mean, you still have to know the total mass of the planet, your mass, and the big R of the planet. Okay, and so for the last case, something that doesn't actually happen in the universe is we have a shell planet where R is still less than big R. So this means that all of the mass is concentrated around the outside of the planet, and you are somewhere in the middle here. Well, I mean, not in the middle, but in the planet. Well, it's sort of the same as this case up here because you have a lot of mass that's over here that you're pretty close to, so the force of attraction is going to be much greater than that of the force of attraction from the mass that's over here that's much further away. However, just like in this case up here, there's a lot more of the mass that's down here that has less attraction than there is of the mass that's up here that has more attraction. So they effectively cancel each other out, and since there's no mass on the inside here in between you and the middle of the planet to make up a force of gravitation, the force of gravitation is equal to 0. So if you were inside of your spherical planet here, you would just float around and not go anywhere unless you were pushed off the walls or something. And that's all I have. So this has been Dane Sholin with the gravitational potential energy derivation and application with planets and satellites and inside of planets and escape velocity. Thanks for watching.